So let's start with a brief recap of where we were. But even before that, let me remind you that you can ask questions on the chat, and Thomas will collect them and maybe interrupt me along the way if there are like there's a critical mass of questions. Okay, so yesterday we, after motivating a little bit what we are going to do in this course, we introduced basically some basic terminologies about the relations, but we also introduce the class of computations, the class of values, and on top of them, a type system that allows you to conclude that a computation has a type and that a value has a type itself, and then on top of typable terms, particularly on top of closed typable terms, there is this notion of operational semantics that we gave. And just to quickly remind you, this operational semantics is pretty standard. If you, for example, try to compute the operational semantics of lambda x, better of a return lambda x, and it is nothing more than the identity itself. Let's call it I. And then if instead you try to compute the return of the application of the identity to itself, well, you get I, because the identity is applied to itself. On the other hand, if you try to compute the return of lambda x, identity x, so the eta expansion, well, this operational semantics is being weak. It doesn't reduce this lambda abstraction because it doesn't look in the scope of lambda abstractions, and indeed it returns nothing more than lambda x, ix. Okay. Now, we would like to do what? We would like to start from this language and define notions of program equivalence or program refinements. That's our objective. Okay, so the point is that we don't want to stick to just one notion of program equivalence or one notion of program refinement, but we would like to understand what are the properties that arbitrary relations should have to be considered good notions of program equivalence and refinement. Okay, so like the desiderata are the following ones. So first of all, well, if we talk about equivalences, yes, equivalences, then, well, we are talking about relations which should be equivalences. That's it. Very good. So transitive, reflexive, and symmetric. No way. But there is something more. Well, behind the scenes, when we were looking at the example yesterday, we were implicitly considering compositionality. If you remember, we were looking at this picture in which the component A and B being equal can be put in a kind of in all possible context, and this way you get a full a pair of possibly complicated systems which are themselves equivalent. And so the fact of being stable this way, of being robust in such a way that allows you to propagate equivalence from components to full systems as an aim, and it is called compatibility. We want to deal with relations which are compatible. And this is also true for refinements. You also want is it the end of the story? Not really. We will see today that compatibility is a too weak a notion, and we need something more. In particular, we want to impose what we call adequacy and pre-adequacy. Okay. So at the level of equivalences, you want also adequacy. And at the level of refinements, you want pre-adequacy. What does it mean? With adequacy, we mean that the behavior of two equivalent programs should be the same. The immediate behavior of the two programs should be the same. But this is not really the same thing as one captures with the operational semantics. It's not at all true that the two equivalent programs should have the same operational semantics. If you, for example, look at this example here and this and this example here, well, they look pretty different from the point of view of the operational semantics, because on the one hand you get the identity, on the other you get an ita expansion of it, and of course ita sounds like a pretty reasonable equality between programs, but the two values are syntactically different. So why is ita good? Okay. The point is that adequacy and pre-adequacy will be formulated only with the reference to ground types, as we will see. Okay, wonderful. So compatibility, adequacy, and pre-adequacy. Let's take a look at how this can be formulated. Okay. So the first thing we need to do is to generalize a little bit the notion of relation and turn it into the notions of term relation. So first of all, you have what is called a closed term relation, which is nothing more than a pair A where R lambda is a family of relations where R is a relation between and itself. So each such relation is a relation between closed terms of the given type, and similarly for R. The only difference is that we talk about values and not about computations. Why are we doing so? Why are we taking not just one relation between values or computations, but a family, actually two families of relations? Well, we do that because we don't want to compare programs which have different types. This simple type theory doesn't make too much sense. Of course, if you switch to other notions of type system, well, it makes sense sometimes to compare terms of different types, but in this particular case, it doesn't. Okay. So this is what people call a closed term relation, and that's why, and that's the way we will compare closed terms. But sometimes, of course, you want to be able to also compare open terms because you want to be fully compositional. So you want to be able to substitute an open term inside a very complicated closed term with another open term, provided these two are equivalent. And then we also need a notion of open relation, or sometimes this is also called a term relation. And in this case, I'm sorry. In this case, you need more in the sense that each sequence in the form gamma sigma, the relation also assigns a corresponding relation are on what? On terms, on open terms of this type, and a relation. This is called the computation component of the relation, and you also get the value. So for each possible environment and for each possible type, you get a different relation. In particular, these are relations on types which are typable in the environment and which have the given type sigma. Which are typable in the environment gamma and as the actual type sigma. We only have one little requirement about the notion of open term relation, and which is that these relations must be stable by Witten. For example, it must be that whenever you have that relation F type sigma, and that's the notation we will use, by the way. Well, you also have that the same computation E is in relation with the same computation F with the same type sigma when we extend a little bit the environment by some fresh variables, which of course do not occur free in either E and F, because otherwise the premise would be completely meaningless. Okay? By the way, that this is the open termination we are talking about, and that's what we are talking about here. Okay, so open termination is a way to compare terms which possibly contains three variables. And well, once you have closed term relation and proper term relations, well, you can play with them exactly the same way you play with ordinary relations. That's the point. So with on open relations, say, you can define following operators. Composition, which is semicolon, and the transposition, which is this operator that we saw yesterday, and of course union intersection. These are, by the way, defined just type by type. if you, for example, take the union or of two closed term relation or of two open term relations, you just take the union of each of the components of the relation pointwise. Same thing about relation composition. You just take the usual relation composition component by component. Same thing about transposition. Okay. So you can see term relations as just collections, families of many relations, and whenever you want to play with them, you play with them component by component. Very good. But then, you know, you also want, and this would help us a lot, you also want to define operations or relations which are kind of specific to programming languages. Otherwise, well, you would not, particular, you want to either restrict or enlarge relations or extend relations. And there are like canonical ways to do that, which are pretty useful, and which is just a standard terminology on the, which are part of the standard terminology on the subject. So it's it is worth mentioning them. And for the closed restriction, of a term relation, open is the closed determination RC, such that on computations, you can conclude that E is in relation with the F at type sigma only when, of course, only when in the starting relation, well, you could put E and R in relation in the empty environment. That's the key thing. And the same thing about values. You do exactly the same thing. So this is like a restriction, a way to go from one big thing, a term relation, to a closed term relation. So a relation which just consider those terms. Right? So whenever two terms are in relation with respect to a non-empty environment, just forget that. On the other hand, you also have a way, actually two ways of extending closed term relations. So if you start from a closed term relation, and you often do that, for example, when you define logical relations, when you define applicative by similarity, well, you have a way to extend all these to arbitrary terms. And for example, when you do it with logical relations, you use the so-called open extension. Actually, with applicative by similarity, use open extension. So the open extension of a closed term relation R is term relation RO, which is open term relation such that when you want to conclude that vector of variables, vector of types, E is in relation F, okay, type tau. Well, you want to be sure, and that's the premise, that for all vector of values, each of them having type tau, it holds that E, where B, so X is in relation to F V of X. And the same thing about values. This is, by the way, just about computations. So the key thing here is what? It's the fact that this V is the same as this V, right? That's why I said wrongly at the beginning that it was what you do in logical relations. This is not what you do in logical relations. What you do in logical to define logical relations is rather the so-called substitutive extension. Substitutive extension of closed term relation R. It is term relation again, which we call RS, such that very good. Still, you want to be able to say when E is in relation U in the new sense F times sigma. Well, and to do it well, you don't play with E, V, X, and F, Vx, but rather with Wx. Require them to be now. And you of course want to say something about V and W. They have to be component by component in relation according to the value part of the starting relation and type. Okay. And this must hold each of type. Okay. The same about values. And again, this is different, right? Because what you get here and what you get here is.
There is a question if,
yes, please.
In the conclusion of open extension, a superscript O is lacking.
Yes, absolutely. Thank you very much. Here, of course, O is lacking. Absolutely.
That's all now.
Thank you. And then, that's not the end of the story. There is another very nice and very helpful way to combine term relations. So you not only have canonical ways of going from closed term relation to term relations and vice versa, you also have a way to combine term relations. And this will help us in giving very compact definitions and also to simplify proofs. And what I'm referring to is the notion of a substitution of a relation into another. So if you have two term relations, call it R and S, okay, you can define substitution RS, okay, as the relation, okay, the term relation we put in relation terms which can be obtained by taking terms which are pairs of terms which are in relation according to R and substituting inside them terms which are in relation according to S. Okay, so you just take open terms which are in relation according to R, and you substitute inside them open terms according to S. So if you, in other words, want to conclude that a certain pair of terms are in a relation according to RS, well, you need to, since computation, you need first start with a term E and substitute a bunch of values inside it, and a term F, computation F better, and bunch of terms. But you need to be sure that on the one hand, E and F are in relation according to R, and I forgot to mention, of course, you also need that X is a free variable in E and F, underlying environment, and then you also want to say that vector V and vector W are in S. And the same thing about values, nothing changes. Okay. Very good, we are almost there. First of all, before going to the key notion, we want to define what it means to be for a term relation to be value substitutive. So the relation is value substitutive. When it is such that Ri is a subset of R. So this is a very simple way of formulating value substitutivity. What does it mean? It means that whenever you start from something in relation with R and you substitute some of the free variables in it with identical values, you still get something in relation according to R. So that's the usual notion of value substitutivity, only it is formulated with the help of the relational calculus in a very simple way. And key notion, even more important notion called substitutivity proper. Tells you that this included also. So the substitution of R into itself is included in R. So when you take terms in relation and you substitute inside them pairs of terms which are themselves in relation, you get something in the starting relation. So these are all properties that we would like to own, right? Because this brings you very close to a notion of compositionality. And finally, we can give the notion of compatibility. Compatibility tells you that whenever you put by the way, I should be clear, but let me stress that this is the identity relation. Okay. So it is the relation which just put identical terms in relation. And the identity relation also plays a key role in the definition of compatibility. Compatibility tells you, remember the picture from which I started yesterday. Whenever you have two things in relation, A and B, and you put them inside any term, any context, any environment, and the C was the same in the left-hand side and the right-hand side, you get two things which are still in relation. And you can easily formulate it by saying that IR is a subset of R. There's nothing more than that. There is another way, you can find it in the notes, but I don't want to spend too much time with that. An alternative definition of the same concept by way of the compatibility refinement. R hat of any termination. The compatibility refinement tells you that basically, let me just write it informally, that you know, if you want to prove that two terms like two terms which are obtained by combining tuples of terms here, tuple of terms here are in R star. You need to be sure that each term, and here the emphasis is on the fact that C must be the same. So when you define the compatibility refinement of validation, you require the two-term validation to have the same topmost operator, to start at the topmost level with exactly the same operator, and then down you can play with R as much as you like. But the at the topmost level, the two operators must be exactly the same. This way, you can give the alternative definition of compatibility in a more, if you like, as a form of a closure operator, because you just say that a relation is compatible if its compatibility refinement is a subset of itself. And that's it. Okay, so we have at least defined what compatibility means precisely, formally. Okay, and that's quite nice because this is like the first kind of property that we really want to have about the relations. Let's go to the other one, adequacy. So a term relation is adequate if and only if whenever, and that's it, this is quite important, whenever you have the two computations okay, are related at the type bool, nothing more, okay, then the operational semantics of E must be exactly the same as the operational semantics of F. So this tells you that for a term relation to be adequate, well, you just have to look at what happens at the ground types. It doesn't matter about what happens in like higher order types, and that's quite close to what, for example, in Bob Harper's book, Bob calls the Pliny equivalence. But in Pliny equivalence, well, you require precisely that the two terms have exactly the same operational semantics. Here, we only ask the operational semantics to be the same at the type of booleans. Okay. And the same term relation R can be said to be pre-adequate. If and only if. Well, with the same hypothesis, but it doesn't necessarily hold that the two values, two semantics values are the same. Actually, one must be smaller or equal to the other one in the sense of the values of partial functions. So if one of the two terms reduced to true, then also the other reduced to true, but not necessarily vice versa, and the same for false. Okay, so compatibility adequacy means being a congruence. The key notion we want to always have to always work with the equivalences which are actually congruences. Compatibility with pre-adequacy, well, it is like a laxer. It corresponds to a notion of refinement. The term on the left-hand side can be less specified than the term on the right-hand side, and this is captured by the notion of pre-adequacy. The fact that we don't require anything about higher order types corresponds to the fact that all higher order values are considered as identical. We don't observe anything about higher order values. We just observe termination, but in this calculus, as you know well, we have a strong normalization theorem, if you like. All terms are terminating. I should have mentioned that. You can find it on the notes, but the absence of recursion, as you probably know, means that all terms reduce to a value. So the operational semantics is actually a total function, not just a partial function. And then, well, these are requisites. Adequacy and compatibility are just requisites. So why and how could we proceed when looking for complete relations? Well, that is a nice result. You can find the details on the notes, which tells you that there is a largest compatible and adequate term relation. So you can find the best compatible and adequate term relation. You can do that because the set of all compatible term relation is a complete lattice. The set of adequate term relation is not a complete lattice, but it has some nice algebraic properties. So, result, let me call it. There is the largest compatible and adequate term relation, which is called contextual equivalence. Contextual equivalence is denoted this way. And analogously, there is largest, compatible, and pre-adequate. Which is the so-called contextual pre-order. You know, in the literature, you can find many different, many different ways to call this relation. The terminology is a bit ambiguous. For example, you often find the notion of observational equivalence. This is precisely what we are talking about. A way to define a very concrete way of defining contextual equivalence is the one I'm going to show here. You can say that terms contextually equivalent if for all context C, which takes terms of type gamma, sigma, and which has Boolean type, semantics of CE is the same as the semantics of CF. And you can easily prove that that's the point. That's the a perfectly equivalent definition of contextual equivalence. That's the terminology we will use, by the way. Contextual pre-order. So if there is like a wonderful notion like contextual equivalence, why should we bother about introducing other ones? After all, you know, it has the properties we like. It perfectly support compositional reasoning. You can substitute contextually equivalent terms inside arbitrary context, and that's works perfectly. On the other hand, the relation is adequate. So why do we bother about other introducing other other notions of equivalence? The point is all here, if you like. So this is bad. This is bad because whenever you want to prove that two terms are equivalent, two computations are equivalent, E and F are equivalent, you need to consider all possible contexts. And yes, that's very burdensome. There is no like a easy and a simple proof principle, and that's why people have been looking a lot at alternative notions of equivalence. Maybe it's a good time to take some questions.
There's one question, maybe we can paraphrase it. Is in our total calculus adequacy and pre-adequacy the same?
Yes, absolutely. Yes, I forgot to mention that pre-adequacy and adequacy in this particular calculus, well, they collapse. But in general, since we, for example, even today, we take a look at recursive types, well, the two things will not be the same in presence of recursive types. So in this case, absolutely yes. In general, are there other questions?
Okay, thank you. I don't know if there are any other.
So let's go on. And, very good. So the research community in programming languages since the 60s, in particular from the 70s, have been looking at alternative ways of giving notions of equivalence about programs, which maybe and hopefully are still compatible and adequate or pre-adequate if you're talking about pre-orders or refinements, but which are more manageable, okay? Which are more manageable than contextual equivalence. And one class of equivalences that I will not spend too much time about, but that should really be mentioned, are the denotational equivalences. Okay. For example, in this particular calculus, there is a very standard and easy way to define denotational equivalence, because there is a very standard and easy way to define a denotational semantics. So you can interpret first of all types, and that's why we actually use the E for the operational semantics. Well, the interpretation of unit is just a set, and it's a set which contains the one single element. The interpretation of pool is just a set containing false, true, and interpretation of pairs just it's just a Cartesian product, set theory, etc. And I'm sure you can see that all the terms in this language can themselves be interpreted set theoretically, in particular whenever you have that x1, sigma 1, xn, sigma n types with type tau. Well, you can give the denotational semantics of E as let's see, as a function going from addition of tau 1 times addition of sigma n, sorry. So the interpretation of any computation of this type becomes a function, okay, a set theoretic function, and this allows you very easily, okay, to define two term relation for Extensional Equality, such that well, if you want to conclude that E is in denotational is in relation to F denotationally, well, you just compute the meaning of E and you compare it with the meaning of F, and you require them to be the same. And in the very specific case of the simplified lambda calculus, you have that the two coincide. particular, the notational equivalence is the same thing as contextual equivalence. I don't want to give all the details about it, but we should keep in mind that this is a very restricted setting. This is the case. This is what people call say full abstraction of set theoretical semantics in the simplified calculus. The bad thing about it is not that not at all the fact that it's based on the notational semantics. Absolutely, it would be wonderful to have these kind of results also for more powerful languages. But the point is that as soon as you start playing with the underlying type system and add recursion at the level of terms, recursion at the level of types, polymorphism, well, things become much more complicated, and getting notions of the notational equality, which coincide with contextual equality, is much more complicated. On the other hand, the notational equality is by construction a congruence. In particular, it is compatible and it is an equivalence. So there is nothing deep about it, and this scales up very well to more complicated languages. So very good. Let me now switch quickly. I don't want to spend too much time on the notational equivalence. Let me switch to logical relations. You already know about it, but let me just put them in kind of in this context. What are logical relations if you think about them as notions of program equivalence? Well, logical relations are term relations in the sense that you can define term relation called logical equivalence. As follows. Let me just give up, just a few, very few cases of the definition, which goes by induction on types. I think you already know about it, because I'm sure you have already seen it last week, so it doesn't make too much sense to spend too much time on it. I just want to. The level of values, you just ask that that the two Boolean values, for example, are the same value, or of course, if you play with the unit type, there is nothing to be proved. It's always odds, and when you have pairs. So, go component by component. Of course, here. And when you this is quite important. So forget about it. You want to compare two value of function type. You do so by just quantifying over all pairs of values which are themselves logically related at type tau. And in this case, you require to obtain terms in the substitution to be themselves logically. Okay, so yeah, at the end of the day, I gave all the cases. No, there is one missing, of course, which is the one about computations. And it's solved by referring to the operational semantics. So, of course, it doesn't make sense. This, by the way, is not really a term relation. It's a closed term relation. Because you only compare closed terms. If you want to turn it into an open term relation, but there's the canonical way to proceed, which is the substitutive extension, which we talked about. And what else? We could spend a lot of time talking about logical relations. I don't think it's worth doing that here. I just want to mention that, as you probably know, there is this theorem, even logical relations, which tells you that logical relation is the same as contextual equivalence. And again, this holds because we are in a strongly normalizing calculus. Sometimes this result is a bit more robust than the one we saw in talking about the notational equivalence, because, for example, if you switch to calculi with just a little bit more expressive power, you can keep it. Otherwise, if you go far, far, far beyond the simple types and the calculus, the result does not hold anymore. And proving that the relation is the relation used by logical equivalence is compatible is not so complicated. On the other hand, proving that it is reflexive is the key. So once you know that it is reflexive, proving that it is compatible becomes very easy. That's the point. And this is the so-called fundamental lemma, as you probably know. In the notes, you can find, for example, proofs of the fundamental lemma done by induction, but all the other proofs are done by way of the relational calculus in a very algebraic way. So
maybe one more paraphrase before.
Yes,
this condition for functions is just extensional equality.
Not really, because what the extensional equality means, at least for me, is that you just test the two functions on the same value. Here we tested the two functions on related values. So it's not really extensionality the way I mean it. It's a form of substitutivity, if you like, embedded in the clause for functions, for terms of higher order type.
Mm-hmm. Okay, thank you.
Very good. Okay, so that's what you can say about the simple type lambda calculus, which is a paradise. Okay. It's kind of a world in which everything works perfectly, in which the notational equality is very easy to be defined and very easy to be proved for the abstract, in which logical relations are very, very well behaved and very easy. If you, on the other hand, enrich the calculus with something like recursive types, well, things actually become more complicated. So let's enrich the calculus with recursive types. It would not take too much because we have done almost all in yesterday's lectures. So. So what do you need to do to endow the calculus with recursive types? Well, the set of types stays the same. You, however, need a way to form type fixed points. Okay, so you can form the least fixed point of the type sigma, where the variable t can occur in the type sigma, and indeed you allow t to occur inside the type. And on top of that, you also want to have co-products and the unit for those co-products, so the empty type. Okay, this way, you not only have the products, but you also have the co-products. And at the level of computations, well, you just no, let's talk about values first. At the level of values, you first of all enrich the set of values with the values in left and in right, which mark the left component, the right component of a coproduct of a sum type, the sum sigma plus tau, and you also have a way to fold the new constructor. At the level of computations, you need to have a way to abort into the presence of the type void, a case distinction. And the unfold. It's pretty much standard, I would guess. I think Bob told you a little bit about it last week. About the static semantics, I just want to remind you that the type system can be just generalized by a rule telling you that whenever you want to form fold type mu t sigma, well, you can do it by typing v with the type that you obtain by substituting t for mu t sigma inside sigma itself. And about unfolding, you can proceed as follows. So you can just go the other way around and start from a value of type mu d sigma, and you unfold it such a way that you get exactly the same. Sorry. Yes, there is this question. I saw that. Well, no, in the sense that in this very specific form of recursive types, I'm considering here all types would be closed. Okay. So we take all types to be closed, and closedness is preserved by substitution. So you don't need to have the context, Alex. So it's a kind of a specific form of recursive types, which on the other hand show you that there is something new going on here. There is something strange going on here. In particular, you can still, as usual, define the operational semantics by the form of step-indexed operational semantics we saw yesterday. But for example, you can extend it with those for the unfold of a fold, which is what you can expect. And for cases, case distinction. F is equal to E, where you substitute. So nothing so surprising, but there are like two things which are different here. You still have that the sequence of functions in this form is an omega chain. So you can take the least upper bound, but it's not true that there is one that for every term E, for every computation E, there is a natural number n such that the corresponding function is returns a value. The calculus is not strongly normalizing anymore. And on top of it, there is also the fact that types are not inductive anymore. See, if you look at this type here, you see that even if it is finite from the purely syntactic point of view, the way we use it in these typing rules here and here means that its behavior, its actual semantics in terms of the actual type that this expression denotes is infinitary. In particular, you cannot apply the paradigm of denotational equality and logical relations directly to this setting. So I apply say defining logical equivalence, Extensional Equality. To this calculus is possible, but not trivial. So for logical equivalence, when you need to go to something called step indexing, and this allows you to tame the inherent non-inductive nature of the set of types. So by using step indexes, not really in the form we saw in the operational semantics, but a similar one, you can tame the fact that types are inherently infinitary for the notational equivalence when you need to go to domain theory. So one can define say adequate and compatible denotational equivalences for calculi like this one, but it's very hard to reach full abstraction. It's very hard to define denotational equivalences, to give denotational equivalence for this calculus, which are fully abstract, okay, which really correspond to contextual equivalence. On the other hand, defining contextual equivalence here, it's exactly the same as giving it for lambda st. So obtain calculus. Call it lambda u. Again, on the other hand, easily enroll. For observation. Okay, so I wanted to start talking about applicative similarity today, but I think I'm almost over. So I won't talk about it. The thing we will start tomorrow is this. So tomorrow we introduce a different notion of equivalence. For it's called which is fully abstract. Thank you very much. I think I will take the time for questions, but I don't think there's any, right? So maybe if there is comments, there are comments, I think you can even switch the microphone on now. Otherwise, I will leave you to the break. Now you guys do the break.
Probably now can everyone is
Okay,
allowed to unmute.
Wonderful. Maybe. Wonderful.
Or I can unmute if.
Yes. I don't think it's worth starting with the applicative by similarity today because it's.
So maybe we can.
If you leave a bit of time, people may have a break before the tutorial, which is in 20 minutes.
Yes.
So it's not a problem to finish.
Very good.
Yeah.
Thank you very much for your participation, and I will be on Slack if you want to ask questions. I realize I'm going a bit slower than expected, but I really plan to tomorrow to start talking about metrics. So after applicative by similarity, I will just very briefly talk about the probabilistic case. So the case of probabilistic calculi, how all this can be lifted to case of calculi with effects, and then I will switch to metrics.